So let's say now that you have some inhibition to the enzyme kinetics equations. So now we have instead this inhibition chemical called I. Now it will be competing with the free enzyme in making a complex. So when we make the enzyme substrate complex here, we make product, but sometimes we'll make an enzyme inhibition complex, and this is like not productive at all. This can't be used to make product. So you see now it's like a fight to see who can bind with the free enzyme, and you'll see that the amount of product that you're going to have is going to be reduced based on how much concentration you have. But the thing is, now when you do this set of equations, finding the product formation rate will be different. So let's do it. And again, we just use the same steps. I'm going to be using the fast equilibrium assumption to make the math a little bit easier. So the product formation rate will be the same as before. dP over dt ends up just being K2 ES. So what we can do with the fast equilibrium assumption, we know that this is true. Well, sometimes what we like to do is, instead of using the lowercase rate constants, we can actually just define a big K equilibrium constant. And it's usually defined as something like, Km equals K negative 1 over K1. Like we saw before when we completed the kinetics without inhibition, we saw that this was the Km value. So we can just use that for here. And for this one, we can represent it with Ki, and it has the same meaning as like that. So here we'll get so don't mix up the big K with a little k, so you should be able to see a difference here. And we'll do the same for this equation. So mix up, I'll call this one Km, and this one is the K inhibition. And now we'll do the enzyme conservation equation, and now we have an extra complex to deal with, which is EI. Okay, and now we just substitute everything back in. We'll get, so I'm just doing this in one step. You can work it out to see how it's true. And you'll see the math is not so bad. You just have to work it out. Now, what was ES again? And now we have to like plug this back into ES, and we plug ES into the product formation rate. And then it's ES, K2 ES. Yep. And yeah, it's just putting it back into this equation. And what can we do to this? Let's make sure everything is fine first. ES into that. Yep, it's looking good. And then we can distribute the Km in the denominator. We'll get this. Okay. So what you actually want to remember here is that the concentration of I is assumed to be a constant value, and Ki is constant as well. We'll end up with equations. Again, you know what we want. We want the Michaelis Menton form. We want it to look like this. But what we can actually do is we can combine all of this into K, well, not S, but we can combine everything else into the Km variable. So we can factor that. And you'll see it's very similar to what we had. You can see that this is clearly like a different case of the basic enzyme equations that we got without inhibition. You'll see that, oh, this looks very similar. So we factor that. And it actually looks very nice. Remember that Km, the Michaelis constant, it's not proportional, it's inversely proportional to the reaction. So what I mean is that if you increase Km, you decrease the maximum, you decrease the reaction rate basically. And if you have a lower Km, then it's better. So it's actually like it's reversed, it's inversely proportional. So you'll see here, if we add a constant I and we add Ki as well to this, it's going to end up being more than what Km originally was. And you'll see that since it's more than what it originally was, you can see that with inhibition, competitive inhibition, the reaction rate will be lower than if the inhibitor wasn't present at all. So now we can call this K2E0 is just Vm, and then we can do that S. And then for the bottom, we can actually call it Km apparent. So we lumped all of that in, plus S. Okay, and it's solved. And you know, it makes logical sense, because if you're adding inhibitor, and the inhibitor is, if it's competing with the enzyme, then obviously, yeah, you're gonna have a lower reaction rate no matter what. And the cool thing is, you can check to see if it's right. If the inhibitor is there, like let's say you remove inhibition, then you just get what you originally got before, like as we described before, the fast equilibrium enzyme kinetics, but without inhibition. Like you set it to 0 and you recover what you got before, and you'll see that, yeah, it's very simple case. It's not so bad to do. You just follow the basic rules. Like only difference is that maybe you have an extra complex here that you have to make sure that you don't forget to add that there. And you also have to write, the corresponding equation for the complex formation rate for the enzyme inhibitor complex. And otherwise, it's not so bad at all. You just work it through, and the math is not bad at all. Hope you enjoyed the video.